Welcome back to our session. We're still talking about oxidation numbers. Now, we've taken time to actually look into, the different rules that we need when we actually apply, these rules of assigning oxidation numbers. But now we want to use practical examples, to try and apply these rules and see how exactly we put them into, practice. Right. So application of these rules for assigning oxidation numbers. Let's consider a substance like hydrogen sulfide. Now, first things first, hydrogen sulfide is a pure substance. What is a pure substance? A pure substance is an element or a compound. And immediately we talk of an element or a compound as a pure substance. What does the first rule say? It says to us that the total is equals to 0. So if you've got an atom of an element, the oxidation number total is equals to 0 for that particular substance. While again, if we have a pure substance in the form of a compound, the total oxidation number for that substance is equals to 0 as well. So that's our point of, of takeoff. Right, so we want to find the oxidation number of sulfur in hydrogen sulfide, okay? Now let's go through the rules and how we best apply them and try to understand that specifically. So hydrogen sulfide is a molecule, right, of a compound. We are fine with that. As a result, the total of all oxidation numbers is 0. That's our first rule that we have to recognize in this case. Right, so we'll assign oxidation numbers to each unknown atom in the compound. So total is equals to 0. That's what we know by now, right? And then what else? We are saying the hydrogen atom, because there's a specific rule that talks about the hydrogen atom. So any hydrogen atom, except in a peroxide, we are saying, in a hydride rather, we're saying that it has got an oxidation number of +1. So the unit oxidation number of hydrogen is +1, right? Now in this molecule of a compound, there are 2 hydrogen. So if we multiply 1 by 2, you'll get the total oxidation number for hydrogen as +2. So if the oxidation number of sulfur is unknown, what is it that we know by now? We know the total oxidation number, or we've managed to come to the total, or to get the total oxidation number of hydrogen. We also know that hydrogen sulfide is actually a pure substance, which is a compound. So the total for this compound is 0. So the one for sulfur, if we are going to say +2, plus whatever must give us 0, it means the oxidation number of sulfur is equals to -2, right? So that's how we apply that rule. Okay. Now, if we assign that, then the unit for sulfur in this case is equals to what? 2, right? -2. But there's only one of them. So if we say -2 divided by 1, okay, it doesn't change anything. It still gives us the total oxidation number of sulfur, which is equals to -2 in this combined state. So the unit oxidation number of sulfur in this case is equals to the total, because there's only one atom of sulfur per molecule of hydrogen sulfide. Okay, that's very interesting. Right, now we move on to the other one. We want to determine, by way of applying these rules, the oxidation number of nitrogen in nitrogen 4 oxide. Okay, so we want to obtain that. So this is nitrogen 4 oxide. What are we saying here? We've got N2O rather. Okay, right. So we want to understand that in this molecule, because this is a compound, now the total is equals to 0, right? So if the total is equals to 0, and then what do we know? We know that the unit oxidation number of oxygen in its combined state is -2, right? Okay, so if it's -2, but then we know that if there is only one oxygen, the unit oxidation number of oxygen actually equals to the total oxidation number, right? So if we talk about nitrogen, okay, there is 2 of nitrogen here. So what are we saying here? We are saying in this case, the total for nitrogen, for us to get 0, it means the nitrogen must be +2, okay? Right, this +2 is for the 2 atoms. So this is the total for nitrogen. And then it means the unit oxidation number for nitrogen in this case is equals to +2 divided by 2, which gives us +1. Okay. Why? Because the +2 is the total for nitrogen. Okay, meaning that in this case we've got 2 of them. It means each one of them is +1. Right. So that's how we apply the rule. And then we've got a polyatomic ion, which is the dichromate ion. Right. So the name of this ion is called the dichromate ion. Right. Okay. So we want to apply the rules. So when we have a dichromate ion, we know that the charge on the ion is equals to the total of all the atoms in this polyatomic ion. Okay. So the total, if we can take, for argument's sake, the formula Cr, okay, 2O, okay, 7, and then 2 minus. Okay. We know that the total in this ion is -2, right? And then for oxygen in its combined state, the unit charge is -2, right? So if there is 7 of them, we're gonna get negative what? 14, okay? So -14 actually comes from -2 multiplied by 7. So the total oxidation number for oxygen in this combined state is -14, while the unit charge is what? It's actually -2. So for us to get the one for chromium, we know that the total is that it should be -2. Then in this case, what do we have? We have got, let this one be X for argument's sake, okay, because we don't know it. You can even model it that way. So we'll have 2 times whatever the unit of, so this X is the unit oxidation number, right? Which is what we are looking for, right? +14, it should give us the -2. So if we simplify this, we'll get, if we transpose that, it's going to give us what? -2 plus 14, which is 12. Okay, +12. Okay, +12. Okay, so this +12 is actually the total. So in other words, we are saying that if we can put it in a simple way, this is +12. So this +12 is the total, right? So if the total is +12, so the unit oxidation number of Cr in this case is +12 divided by 2, which is equals to +6. That's how we have used the rules to actually obtain that. Because if you say +12 minus 14, it gives us the -2, right? And then last but not least, we have the manganese 4 oxide, right? So in as far as manganese 4 oxide, you do realize that this is manganese 4 oxide, this is potassium permanganate. So all of them are compounds. So in as far as Mn, let's say K, MnO4, this is potassium permanganate. The total is equals to 0, okay? The unit for oxygen is -2, right? Potassium is group 1, +1. Then we're looking for that. So the total for potassium is +1, okay? We don't know for manganese. For oxygen is -8. The total from -2 times 4. And then what is it that we do to this so that we get 0? It means it is +7. So the unit oxidation number of manganese is +7 in this case. What about in manganese 4 oxide? MnO2, right? So the unit for oxygen, -2, right? And then the total is 0, because this is a pure substance, which is a compound. So in combined state, oxygen is -2, but there's 2 of them, so the total is -4, right? Then in this case, to get 0, what must we do? This is +4, okay? So the oxidation number of manganese in this case is +4. You do realize that in this compound, potassium permanganate is +7. In the other one, manganese 4 oxide, it's +4. This is a transition metal. Its oxidation number can change, all right? That's what is so special about transition metal. So in closing, we are saying that atoms of the same element can have different oxidation numbers when they bond differently with substances. Okay, so these are some of the examples in as far as applying the rules for assigning oxidation numbers. We shall take a short break for now. When we come back, we'll look at more practical examples so that we can apply these rules. Let's take a short breather for now.